Whenever you're ready, sir. Whenever you and Gunjana are ready.
I'm fine. You can start.
Should we start, ma'am, or?
Yeah.
Okay. So good evening, everyone. We welcome you to the IN Statistics series. The only idea is behind this is because we are getting too many requests related to the statistics learning, and already NNF under the leadership of Dr. Sourabh Dutta sir is already running a program for a journal club with a lot of learning related to the basic statistics also associated with that. So this session, we will be focusing mostly on a whiteboard teaching. So we don't have any slides as such. So it's more of an interactive session. And for this, I welcome Dr. Femitha, who is from Department of Neonatology. She is a senior consultant. And of course, as a moderator, we have Sourabh Dutta sir, who doesn't need any more introduction. So we will not delay the session. And I think over to you, Dr. Femitha ma'am, and we can just start with the session.
Sourabh sir, would you like to say a few words, sir?
No, I think go ahead. I'll just butt in if any questions come up from the audience. And
Okay, sir.
yeah.
I will just open my slides, sir. My screen is visible?
Yeah.
Yeah. So like Gunjana said, this is only an interactive session. And I just titled it as Biostatistics for Exams and Bedsides. And we thought we will start with diagnostic test performance indices because it's there in bedsides as well as in the exams, which is quite a useful and important topic for the exams. I am focusing on very basic fundamentals here, and I have just got you to do some calculations on your own while you're listening to us. And you also can ask questions. Sir is there. If, whatever I don't know, I will ask her to answer as well. So here goes. The objectives today, what I mean to share, is to learn the meanings of some fundamental terminology that is associated with what constitutes the performance indices of a diagnostic test and use some simple mathematical examples for us to understand this better. And then how would you use this information in practical life as well as in exams and viva? So this is it. I don't have anything to declare. Yeah. So the first thing is that we need to understand in which situation we need to use diagnostic tests. It got a little interesting yesterday because when Gunjana asked me to test out the whiteboard method with my iPad as the remote, my Mac was completely failing to pair. And so when I took it or I called the Apple Center, they said we need to do a diagnosis. So it really was an anticlimax for me. And they did a diagnostic test analytics running all over the place. And then they told me, so yeah, this is what is your problem and this is how you're going to solve it. So yes, diagnostic tests we know are used for screening. That would be in a general population of normal population apparently, and you will find out whether they are more at risk of disease or whether they actually have the disease per se or not. Then it's also used for finding out whether the disease is there or not. That is to find out whether you confirm the disease presence or to rule out the disease. It is also used to find out what is the severity of your disease, like what stage you are in and what course you're going through, and it also helps in finding out some degree of prognosis. So diagnostic tests, even though the term used is diagnostic, there are multiple ways in which tests as such can be used. So why I've introduced this is because the various terminologies that you're going to listen to in performance indices will come in due importance where you're going to use the diagnostic test. Like for screening test, we have a set criteria of how much should be certain things. And for a confirmatory test, you have certain things that have to be satisfied. Yes. So the first terminology that all of you must have heard of, and most of you would already know, this would just like a revision for you, is that you would have heard of sensitivity and specificity, right? So here, like everything else in most biostatistics, you have a 2 by 2 table and you will have to draw it out for yourself. Now, here you can actually keep your calculator handy, or if you're very good at math calculations, then straight away inside your head. I just have one or two simple mathematical examples for you. Whenever you draw your 2x2 table for any test, you have to put the disease up there. This is basically so that you get some uniformity. There's no such rule that you have to have the disease up there and your test has to be here or the test results have to be here. It's just for uniformity because most of the literature will work this way. So when you say disease, nobody knows whether the patient already has a disease or not. So when you say whether disease is present or absent, it is usually meaning that the gold standard of that particular disease diagnostic test is positive or negative. So here, what test you're going to talk about is called as the index test, or sometimes it's a new test. It needn't always be a new test. It can also be a test that you want to select for diagnosis of or screening of a particular population. So this depends on what scenario you're sitting in. If you're sitting in bedsides and if you want to find out if a particular patient has sepsis or not, you're going to do a test, say a CRP or a blood count or a platelet count or something, and you want to compare or you want to see whether disease is there or not. Now, disease is there or not is decided by a gold standard, correct? You may think that it's sepsis, it need not be sepsis. So till now we know that sepsis gold standard is probably blood culture. You have molecular diagnostics coming into the picture now. So when you say disease is there or not, nobody has told you whether disease is there or not at that point of time. What you're actually comparing it to is a gold standard test. And the test that you are talking about, diseases that you're talking about, is basically the index test or what test you are going to select. Okay, so there are 4 possibilities that can come when you have a 2x2. Gujana, I guess if you're host, you'd be able to.
I am unable to do it, ma'am. I'm trying. And I'm not a host. You are still the host.
Oh my goodness. Okay, then I'll have to bear with this. Yeah. So if you have the disease, you have 4 scenarios, right? So disease might be there, disease might not be there, which means the gold standard is positive or the gold standard is negative. And the test result the test that you're talking about, that test can come out as positive or come out as negative. Now, this pattern of putting the plus here, the minus here, the plus here, and the minus here is also kind of a standard. It doesn't have to be like that, but it makes it easier to understand because most of your other textbooks will give it to you in the same way. So what is the best case scenario? That every time that the patient has the disease, the test should come positive, right? And every time that the patient does not have the disease, the test should come negative. That is your ideal situation. But unfortunately, that's not the case. You will have certain situations where the disease is not there, but the test will come as positive. So that would be this situation. So where the disease is not there, but the test will come as positive, and that would be your false positive, correct? Right? And so this would be your true positives, of course. And there will also be another situation, invariably, where actually the disease is not there and your test is negative. That is your true negative. But you will get some situations where you will get test negative irrespective of, in spite of the disease being present. So that would be your false negative test result. So the test has come negative, but the disease is actually there in the patient. Now we will flip and remove all this TP, FP, FN, FTN, and they will put on only numbers so that it makes it easier for us. So suppose you have a particular disease and you're going to test a particular test. That is your index test or the test that you're going to select. So you can have, say, 100 patients who have the disease and 500 patients who don't have the disease. Now, we are talking about something in retrospect. This is not what happens in real life. This is when you're actually finding which test to select in a particular situation. You don't already know whether disease is there or not in the case of a bedside practice. But you will know that if you're testing a diagnostic test, like if you're doing a research study to find out if a diagnostic test is good or not, or what are the parameters. So if you're standing bedside, you do not know whether disease is there or not. But we'll start with the standard order of sensitivity and specificity, where you're actually using it to select a particular test in a given situation. You use these parameters of sensitivity or specificity to select a particular test, whether that test in that situation is good or not. So suppose you have 100 patients who have the disease, that means the gold standard test would have turned out positive, and you have 500 patients who do not have the disease, or the gold standard test would have come out negative. So disease here, I am equivalent, giving it an equivalent as the gold standard result. Okay. Yeah. So like, for example, if you're thinking about some screening test for CA lung, then the biopsy or histopathology of the sample when taken out operatively would be the gold standard, which will tell you whether disease is truly there or not. So that is one situation. And suppose somebody found out a new test for diagnosis of or for screening for CA lung, like you measure something from the exhaled gases and you see whether it's actually giving you a good predictive value of the diagnosis or not. So this is the index test results that you're going to get. Now, suppose out of these 100 patients, you get 90 of them coming positive in the test when the disease is actually there, but there are 10 of them who have the disease but test negative from your index test. Okay, so out of 100 patients, 90 of them have tested positive by your index test, but 10 of them have unfortunately tested negative by your index test. Just like that, if you have 500 patients who do not have the disease, and you have, say, 400 of them have tested negative by your index test. Okay, sorry. 400 of them have tested negative from your index test, but unfortunately, there are 100 of them who have tested positive in spite of not having the disease. Now, from this example, we will together calculate what is the sensitivity and the specificity. Okay, so for that, let's just go to the definition of sensitivity in true sense of just English. We will not talk about it in terms of statistical jargon. That is, we will not talk about true positive, false positive, true negatives and all that. What is sensitivity? Sensitivity is out of the entire diseased population, how many of them are going to test positive by your index test or the test that you are going to select. So the denominator is out of all those who are diseased. Okay, so the denominator in this is all the diseased population. Out of that, how many of them will get a test positive? That is your sensitivity. Okay, so if you go back to your table, you will find that out of all those who have got the disease, how many of them have tested positive? So what would that be? Out of all this who have got the diseases, 100, right? And how many have tested positive? 90. So your sensitivity here will be out of all those who have the disease, how many of them have tested positive? So the sensitivity of this particular test that you're talking about on the left side of your 2x2 table, that is this test, is 90%. Okay. Similarly, if you were going to talk about specificity in true language of only English, okay, then it would be out of those who do not have the disease. So that is your denominator. How many of them will have a test result negative? Okay, so we need not have to put in TP, FN, FP, TN and all those things. So like we said earlier, sensitivity is out of all diseased, how many are tested positive? Specificity is out of all those who do not have the disease, how many get test negative? So from your table, how much would that be? Out of all those who do not have the disease, that is 500, how many have tested negative? It is 400. So you will get out of 500, 400 have got test negative. So here it will be 4 by 5 into 100 because all of them are by proportion. So if I make a mistake, please tell me. Yeah, so your specificity is 80%. So what does it mean in real life for you? Okay. In real life, we can use the same thing as, I'll put in two terminologies which are used, called snout and spin, and come back to it 2 minutes later. So what is the meaning of sensitivity? It means that you will actually, if it's a highly sensitive test, then which means that out of all the disease population, you're likely to pick up many of them or most of them. But in the process, you might end up testing positive for some people who do not have the disease as well. So you might have some false positives. So high sensitivity means that you will pick up everybody because the proportion of those who get test positive out of all those disease is going to be quite high, but you might end up getting a few false positives because it's a very sensitive test. But if it is a specific test, it means that out of all those who have no disease, many of them will have test negative. So if you have a test which is positive, a highly specific test being positive, then you can almost be sure that the disease is actually there. Okay? Because you will almost always be sure that the patient has the disease. So your chances of diseased getting test negative is going to be very, very less. Okay. So it sounds a little confusing here, but to think about it, you will find that, we'll draw it out in a graph now. You'll find that a highly sensitive test is going to pick up everybody. But if it turns out negative, then you almost always rule out the disease. Okay. If it turns out positive, you'll pick up most of the patients, but you'll also find some patients who have not got the disease but will still get the test positive. So if you get it negative, then you will rule out the disease if the test is a very highly sensitive test. But if you have a highly specific test, I remember it like this, SP, highly specific test positive, then you're almost always sure that the disease is there or it rules in the disease. Okay, these are two things that you can find out. Now, suppose I give you an example that in the general population, this is the distribution that you get for a particular test result. Okay, and you say that, say, CRP test more than 5, I will use as indicative of sepsis. What will happen? You'll pick up a lot of the general population also getting more than 5 because it is a low number. If you're going to say that you're going to raise the threshold of your test positive to a threshold of 10, if the CRP is 10 only, I'm going to take him as sepsis, then you will get lesser number of the normal population getting a test positive, okay, which means that you have actually decreased the sensitivity of the test result. If you go higher and higher, then very little of the normal population is going to get a positive result, which means that you're not going to get too many false positive results, but you might end up missing some, because always sensitivity and specificity is like a balance. If you're going to go up on sensitivity, you're going to go down on specificity. So this is the corollary of what we said just now. If you're going to use something that is as low as 5 as your as your cutoff for CRP for diagnosis of sepsis, then you will pick up all the sepsis, because most of the sepsis will have results which are CRP more than 5. But you will also find a large number of the normal population of babies also getting CRP 6, 7, 6.57. So you might get a lot of false positives. So you can be sure that if it is negative, then you have ruled out, which means that the CRP is less than 5 or 4. Then you're almost sure that this patient doesn't have sepsis. So highly sensitive test negative will rule out the disease. Does that make it easier to understand? So if you have very specific tests, so suppose I say only those who have CRP more than 50 is going to be sepsis. For me, for my definition, more than 50 only I'm going to treat as sepsis. Then I'm not going to pick up any normal babies, because hopefully most of them will have CRPs less than 50. So I will not get any false positives. But in the due course, you will pick up the true sepsis fellows. So if it is really positive, if a highly specific test, like if you use a CRP cutoff of 50, a highly specific test getting a CRP of 60 above 50 will rule in the disease for you, but you will miss out a lot amount of sepsis babies, which means that the sensitivity has dropped in the process, but the specificity has gone up. So I'm just going to go back to tell you these two again. Remember it in simple English, even when you're asked in the exam. Instead of saying true positive divided by blah, 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 you say sensitivity means that out of all those who are diseased, how many of them will come test positive for that particular test is called as sensitivity. And specificity means of all those who are non-diseased or for whom the gold standard is negative, then how many of them will, out of these, how many of them will get test negative is called your specificity. And both are a balance. So if you get high sensitivity, usually you will drop the specificity a bit. The best test, of course, is 100% sensitivity and 100% specificity, which is not going to be possible in real life because it doesn't happen. You'll have to strike a balance between these two. Now, striking a balance between these two, we will do little bit later. Before that, we will talk about two more terminologies that are very common in the exam as well as on bedside. One is positive predictive value and the other is negative predictive value. Now, again, this also we are going to do with simple English only. We'll draw again the 2 by 2 table for you. Okay, so this is disease present, disease not present, test result positive, test result negative. We had 100 diseased and we had 500 non-diseased. Out of that, 90 diseased fellows, out of 100 diseased people, 90 of them came test positive and 10 of them came unfortunately test negative, which is not correct or which is actually a false negative. And out of 500 non-diseased people, you get 400 of them, which is correct, which means you have 400 true negative patients, but 100 of them, in spite of not having the disease, get a test result positive. Okay, so this is a wrong result. This is a wrong result, which means disease is there, test is negative. Disease is not there, but test is positive. Okay, we already talked about sensitivity and specificity. So that situation where you use sensitivity and specificity, the denominator is out of all diseased or out of all non-diseased, respectively. That is for sensitivity and for specificity. That is used for selection of test. Like we said, that if you want to pick up all of a particular disease without missing anybody, then you take some test which is highly sensitive. If you don't want to do that, if you want to be sure whether a disease is there when you get a test result positive, then you use a very specific test. Like, for example, if you're going to be saying some other CA, some other cancer, then if I'm going to just look at a particular biomarker, which is not so great in terms of specificity, which means that even if it comes positive, you can't be too sure that the patient has the disease, but at the same time, you don't want to miss anybody because it's a dangerous thing to miss a patient with cancer, then you use a very highly sensitive test. That is for screening of the population. But what are those tests? They should be very easy to do, they should be inexpensive, they should be preferably very less invasive, and it should be acceptable, it should be easily available. So all these are what should be a very highly sensitive test, which is and should be very sensitive if you're going to use it for screening. But if you're going to use it for ruling in a particular disease, like if you're going to be wanting to be sure that if this test is positive, then the patient should have the disease, or should all the disease people should be all the non-disease should be ruled out, then you use a specific test. So for them, it can be a little invasive, it can be a little advanced because they are usually used as confirmatory tests. So the term sensitivity and specificity are usually used when you're choosing the test in a particular situation. But when you're standing bedside and you already have the test result with you, like you're standing there and somebody's telling you in rounds, this is the test result. Now you have to make a decision whether this patient is likely to have the disease or not. So that is where you come into, you use these two terminologies. That is your positive predictive value and your negative predictive value. So PPV, like the word means, positive predictive value. So my teacher says it's better to use it the other way. It is a predictive ability or the predictive value of a positive test. Positive predictive value or predictive value of a positive test. So what does it mean? In this, the denominator is out of all those who have the test result positive, how many actually have the disease? So it's not the inverse, but the numerator and the denominator have kind of become a little opposite to each other. So the positive predictive value is out of all those who have the test positive, how many actually have the disease. So you already have the test result standing in front of you, and you want to now think, okay, is this baby actually having this particular disease or does he not have? So if it's a high positive predictive value test, okay, then if the test result is positive, then you can be reasonably sure that the disease is there. And if it's negative predictive value, it means that out of all those who have test result negative, how many do not have disease? Okay. So for the people who already know, it's a repetition, but for the fundamentals, once more, sensitivity is out of all those who have the disease, how many have test result positive? And specificity is how many who do not have the disease, out of those, how many have test result negative? But PPV is you already have the test result with you. Out of all those who have test positive, how many have disease is your PPV. And NPV or negative predictive value, it makes sense, right? Negative predictive value or the predictive value of a negative result means that out of all those who have the test result negative, how many do not have the disease? Now, what's the big deal about having these two? Can't you just use sensitivity specificity? Okay. Why we use PPV and NPV specifically is because both these things are dependent upon prevalence. That means in what kind of population you're doing the test matters for PPV and NPV. We'll see that. So suppose I'm sitting in the OP and I'm actually doing a well baby follow-up. One patient walks in and she says that there is this for the last 2 hours, the baby has not been feeding well and is looking a little off, little dull or little sleepy. So I look at the baby and say, okay, let's watch, let's observe, because I don't want to straight away go ahead and do all the blood tests and or admit in the ICU. Why am I doing that? Because subconsciously, I know that the prevalence of having sepsis in a well-term neonate who has just come into my well baby clinic is very, very low. The prevalence in that population is very low. So if I'm going to do a CRP in that baby and I find it to be say 11 and my cutoff for sepsis CRP is 10. Okay, so I did the test and I found that this baby has a CRP of 11. In that population, that is in the OP well baby clinic, where I'm not expecting things to be bad, if I get a CRP of 11, I'll think, okay, the test is positive, fine. But is it likely that this baby actually has disease? Not really. So probably the positive predictive value in that population of that test is very low. Okay. Now, if I'm going to sit in the ICU and there a nurse calls out and says that there is this preterm baby who's now day 5, day 6 of life, who has been on central line catheters, is not behaving too well, who's also sleeping for the last 2 hours, and they have done a CRP. Now, if you do get 11 CRP, you might think that this positive result, according to my definition of positive, of 10, more than 10, might be that this baby has higher chances of disease. What am I doing subconsciously? I'm trying to think that the prevalence of sepsis in that population now, where I'm sitting, inside the NICU, inside place where a lot of preterms are there, where HI can happen, where there is overcrowding, where there are central lines, the prevalence of sepsis is high. So the positive predictive value of my test now becomes higher. Okay, so the PPV is actually dependent upon prevalence. The same way, if you have a prevalence that is very low, like in the OP, if I get a CRP negative, okay, the chances of not having the disease is very high because the prevalence is low. I got a CRP of 4, I can be almost sure that this baby doesn't have sepsis. But if I'm sitting in the other situation, say inside the NICU, I got a CRP of 9, which is still negative according to my definition. But the prevalence of disease here is very, very high. So I may not be too sure that this baby doesn't have disease in spite of having a negative test result. So the PPV and NPV are dependent upon prevalence. Can we look at it mathematically? Yes, we can. So we will use the same example. We'll use the same old numbers. You have disease positive, negative, and you have test result positive, negative. You have 100 patients, you have 500 patients without, not patients, 500 good population without the. And in this, you got 90, 10, 400, and 100, right? So this was what our situation was. We already calculated sensitivity and specificity. We found that the sensitivity was out of all the disease population, how many got test positive? That's 90. I'm repeating quite deliberately. Specificity is out of all those who do not have the disease, how many got test negative? That is 400 divided by 500, correct? Which was 80%. Now, let's go to PPV. What did we say PPV was? PPV is equal to out of all those who got test positive, how many actually have the disease? So what is this? Out of all those who have test positive, this. How many actually have the disease? So it is 90 plus 100, 190, and the numerator is 90. So out of those who got test positive, that was 90 plus 100, right? And how many actually have the disease? This. So 90. Now you can do the math. I'm not going to. 90 divided by 190 into 100. That would be your PPV. Keep it aside. One of you will have to tell me the answer. Deepa, you're there, Deepa? Somebody will have to just do the calculation and tell me this, okay? Now, let us look at NPV. What was the definition of NPV? NPV was that out of all those who have test negative, how many do not have disease? That was the definition, right? So the denominator was test result in PPV and NPV. So how does it come now? Now you have out of all those who have test negative, that is 400 plus 10, 410. How many of them got a negative result? Okay, so 410 of them got a negative result. That, oh, sorry. Okay, I just lost the connection here. 1 second. Gunjana, can you see?
Yes, ma'am, it's visible.
Yeah, okay. I just lost the iPad connection. So disease and test. Okay. So again, I'm repeating because I lost it. So you got 90, 10, 400, 100. Okay. So NPV is equal to, of all those who got test negative, that is 400 plus 10, correct? 410. How many of them do not have the disease? That is 400. So 400 divided by 410 into 100. That is your negative predictive value. Can somebody do the math with a calculator, please?
Yeah, we did have a values now, ma'am. Positive predictive value 47% and the negative predictive value as 97%.
Okay. Is that right?
Yes, ma'am.
Yeah. Now, we will now drop the prevalence of disease in the same population. So how many are there in this entire population? You have 90 plus 100 plus 10 plus 400, right? Or you have 100 plus 500. You have 600 babies here. Okay. In 600 babies, you have 100 of them having disease, right? So the prevalence in this population is, in 600 babies, 100 are having disease. Okay, this is the prevalence in this population, which we were talking about so far, where you had this box. Okay, now I'm going to drop the prevalence in this population and then we will recalculate sensitivity, specificity, PPV and NPV and see what happens. So what did I do? I just increased the number of disease negative people in order to drop the prevalence of the problem. Now can we do sensitivity, specificity? Sensitivity is, out of all those who have disease, how many tested positive? Specificity is, out of all those who do not have the disease, how many tested negative? If you will see, both the numbers were the same as exactly what we calculated for this table. But if you look at PPV, it is out of all those who got test positive, that is 1090, how many actually have disease? And out of all those who got test negative, how many actually do not have disease? Now, if you want to recalculate, you will find that the sensitivity and the specificity will remain the same, but your negative predictive value goes up. It's almost 100, right? Right? It's almost the same, the numerator and the denominator. So which means that if you have a prevalence which is very low, then the negative predictive value of your test result is very, very high. So if you get the test negative, you're sure that this patient probably doesn't have the disease in a low prevalence population. You do just the reverse when in your free time. I mean, it's not a nice thing to do in your free time, but still, if you're going to do some math in your free time, you reverse this, increase the prevalence of the disease by increasing this side of the box, that is the diseased population box. You will find that sensitivity specificity may not increase or change, but your positive predictive value will go up, which means that if your test turns out positive, then your chances of actually having the disease is quite high. So what you need to remember is PPV and NPV depend upon prevalence of disease or how common the disease is in that given population. So you're actually doing this in your day-to-day life in a reasonably subconscious manner. Okay. Shall we move on, Gunjana? I finished the 4 basic ones. We're going to move on to PLR and LR.
Yeah, ma'am. We can go ahead.
Yeah. You could tell me when to stop, Sourabh. So whenever, if I'm making mistakes also, please.
No, I think you're doing perfectly well. Go ahead.
Okay, sir. So next 2 things that we need to know, which we actually don't use in day-to-day life as mathematics, but we are again doing it actually in the real sense, is positive likelihood ratio and negative likelihood ratio. Now, these are important for exam anyway, so you might as well know the definition. Here, there will be one pause we have to take in our brain and understand 2 mathematical concepts, which we know. One is probability and the other is ratio. Okay, they're 2 different things. Probability is also a proportion. Okay, we'll use this terminology instead of probability. Proportion means that out of so many, some small portion. So the denominator say is 100, and if you say 90 out of 100, it means that 90 is included in that 100, right? It's not mutually exclusive. So in a proportion, the numerator is contained inside the denominator. That's what a percentage is, or a proportion is, or a probability is. But in a ratio, the numerator is mutually exclusive from the denominator. That's just like how you say odds ratio or risk ratio. The numerator is not contained inside the denominator. Like if I were to say the same thing in terms of a ratio, I'll say it is 90:10. Because something is positive 90 times, then something is negative. The same thing comes negative 10 times. So the numerator is different, the denominator is different. Okay, so till now, whatever numbers we talked about, that is sensitivity, specificity, PPV, NPV are all proportions, because then if you will find all diseased positive, how many test positive, or all test positive, how many diseased. So you will find that the numerator is contained inside the denominator, so they're all probabilities or proportions. But now we're going to talk about two ratios, that is a positive likelihood ratio and the negative likelihood ratio. Okay, so PLR. Okay, now this is a ratio of the again in English only, the likelihood, sorry, not need, yeah, is equal to the ratio of the likelihood that a diseased person gets the test positive as his result, divided by the likelihood that a non-diseased or a normal fellow gets the test positive. We're talking about positive likelihood ratio. Okay, so this is the common factor there. The test is positive in both the numerator as well as the denominator, but you're testing to see if your chances of getting the test positive in a diseased to the chances of the test positive in a non-diseased is what? That is your positive likelihood ratio. So here again, to complicate matters a little more, this is a proportion. This is a proportion. But between this and this, it's a ratio. Okay, so the likelihood that the diseased gets test positive means what? Out of all diseased, how many get test positive? Haven't you heard that? Sounds familiar? Which is nothing but the sensitivity. And the denominator is out of all those who are non-diseased, how many of them will get test positive? Okay, I won't write TP, I will write this, otherwise it will look like true positive. Okay, so out of all those who are diseased, how many will get test positive? That was your numerator. And out of all those who are non-diseased, how many of them are getting test positive? Because we're talking about positive likelihood ratio. So the numerator is very easy. Out of all diseased, how many came test positive is the sensitivity. Denominator is 1 minus specificity. Because specificity is what? Specificity is in non-diseased, how many got test negative. Now we're talking about in non-disease, how many got test positive. So it is 1 minus specificity. Okay, right? This is easy again. Like if I were to tell you 90 out of 100, how am I going to split it and make it into a ratio? What did we do? We did 90:10. 90:10 is nothing but 90 divided by 100 minus 90. Okay, or 1 minus 90 by 100. Okay, so sensitivity divided by 1 minus specificity is your positive likelihood ratio. Once again, PLR is the ratio of the likelihood that a diseased patient gets a test positive divided by the likelihood that the non-diseased patient or a person gets a test positive. That is nothing but sensitivity divided by 1 minus specificity. And does that look familiar again? It does, because that is what we use in an ROC curve. Okay? In maths, the slope of any curve is the y-axis divided by the x-axis. And if I was going to do sensitivity divided by 1 minus specificity, and the graph that you get, the slope of that graph is your PLR, which is y divided by x. We'll come to this a bit later if there is time, why we need an ROC when you actually have a PLR. This is because you have different cutoffs for different tests. All of them are not just dichotomously positive or negative, just like that, unless you're talking about, say, uh, biopsy positive or biopsy negative. It's not like that, right? We have different cutoffs. So if I have a Downey score of more than 3, it means something. If I have a Downey score of more than 4, it means something else. So everything has usually got a numerical value to it, and you have different cutoffs to it. But if you have just a dichotomous test result, you don't need an ROC curve. If you have something that has different cutoffs, then you have to draw an ROC curve in order to find out the best balance between sensitivity and specificity. And PLR is a numerical way of putting that, the best balance between sensitivity or specificity, which is the slope of your ROC curve, that is sensitivity divided by 1 minus specificity.
Femitha,
Yes,
Femitha,
sir.
can I just butt in at this point?
Of course, of course.
Yeah, yeah. So one has to be a little careful when one is making this, conclusion. So what we are actually saying is that the delta x, sorry, delta y upon delta x is the slope,
Slope.
right? So say between two values of the test result, between any two values of the test result, that slab of values, in that slab of values, say suppose you take CRP of 5 and CRP of 10. Huh? So between CRP of 5 and 10, between a CRP of 5 or 10, over there, the slope is the likelihood ratio.
Yes, sir. Yes,
So
sir.
it's the tangent, out there. At that part, the slope is the likelihood ratio, which is the change in sensitivity upon the change in 1 minus specificity. So it's not really the dotted line
Yes, sir.
which you put. So the dotted line is actually the line at which it's a useless test, because at every point, the
Uh,
sensitivity and 1 minus means the false positive rate and the true positive rate are the same at all points of time on the dotted line. So you want a curve which is as far away from the dotted line as possible towards the top left corner of the graph. So the more the line is towards the top left corner, the better it is. And when we are saying likelihood ratio interpreted from an ROC curve, it is basically between 2 points on that curve. What is the slope there? That is the likelihood ratio of between those 2 points. Just wanted to highlight that. Yeah, go ahead.
Sir, I'm sorry for the ruckus happening also. So yeah, um, I'll just clarify one more point which Sir said. This ROC is a useless test, like Sir said, which means that the likelihood of a diseased patient getting positive is the same as the likelihood of a non-diseased patient getting positive, which means the PLR is 1 and it's completely useless. So if a PLR test is much, much, much more than 1, much, 1 second, please, sir. Much more than 1, then only the test is going to be of any use to you. So, just, sir, can you give me 1 minute, sir? I'm so sorry. Just 1 second. So sorry, sir. So sorry. Yeah. So if the PLR is much, much more than 1, then only it means that the likelihood of a diseased patient getting test positive is much higher than the likelihood of a non-diseased patient getting a test positive. So if you get this ratio as 1, that means your test is literally useless. So we prefer that a likelihood ratio be at least 10 or 20 or 100 or 80. Then only it increases the chances that the patient is having the disease if your test results are positive. So if I have a test which tells you that the disease population also may get positive and the non-disease may also get positive in the same ratio, then doing the test is not going to add any benefit to my diagnosis. So at least by 10 times, I should be able to increase the likelihood of the disease in that patient if the test comes positive. Then only there's any point in doing the test. So reverse of that is also making sense. That is a negative likelihood ratio. Now let's define that in English again. Negative likelihood ratio, the numerator and the denominator will have a test negative as the result. So if you have the likelihood of a non-diseased patient, likelihood of a non-diseased patient getting test negative divided by the likelihood of a diseased patient getting test negative. So the common point here is test negative, because you're talking about negative likelihood ratio. The likelihood of a non-diseased patient getting test negative divided by the likelihood ratio of a diseased patient getting test negative will be your negative likelihood ratio. So this, if you're going to have, so did I make a mistake there, sir? This likelihood ratio of a diseased getting test negative on the numerator, right, sir? Sourabh, sir? Gunjana, are you there?
Yes, ma'am. I'm there only. I think you have stated it right. I think Saurabh sir is also there.
Sir?
Sir, there in the meeting.
Okay. So if you have a negative result, you need to have the non-diseased having a much higher chances of getting a negative result. So your NLR should be further and further away from 1. That means lower. So it should be diseased on top. Yes, that's not how it is. Yeah. So if your likelihood that a test negative comes in a diseased patient is very, very, very low, then you have a good test. So then for NLR being much lesser than 1 is good, and a PLR being much more than 1 is good. Okay, so you remember that PLR and NLR are ratios, and we are taking two probabilities on the numerator and the denominator. Now, just like we converted sensitivity and specificity, like you got sensitivity divided by 1 minus specificity for PLR, we're going to do the same thing here. So what would this be? Likelihood ratio of a diseased patient getting a negative result divided by the likelihood of a non-disease getting a negative result. This is what? This is specificity, right? And the top one is disease getting test negative. That is 1 minus sensitivity. This is NLR, correct? So sensitivity was nothing but disease getting test positive. So disease getting test negative is 1 minus specificity. And likelihood ratio that a negative result comes in a non-disease is the same as the specificity. Okay. Now, where do you actually use this? Is it of any use to us? You use it when either serially you do a number of tests in order to be more and more sure that a disease is there, or on the reverse, more and more sure that the disease is not there. Or you may do a bunch of tests together and then say that you are sure or not sure that the error not there. Okay. So you will do multiple tests. Test 1, test 2, test 3, test 4, and you're trying to increase the likelihood that this patient is actually having the disease or not by doing numerous tests either together or one after the other. So that's exactly what you're doing in the OP as well. If you're sitting in the OP and a patient comes to you and tells you that my baby is not feeling well, now, in that situation, you've already made up your mind, okay, that there is possibility that this baby has a disease. Now you examine that patient and you find that, yeah, he's looking lethargic. There is something wrong with him. He's having a little bit of tachypnea. You're finding that he's looking a little off color. In your mind, again, you have done another test, which is examination, and you have increased the likelihood that this baby patient has a disease by doing the test. What is the test? The first test was history, the second test is physical examination. Then after that, you admitted him to the NICU, you did some basic tests, you did a blood count, you did a CRP, and you found that something was wrong in those tests. So you again increase the likelihood that this patient is having a disease. So you did test 1, test 2, test 3, whether it was together or whether it was in tandem, you have increased the chances that this patient has a disease by doing all those tests. Now, suppose in between you do say something that is absolutely nonsensical. Suppose you do say serum bilirubin, even if he's not looking, he's a 1 month old baby. You've just done serum bilirubin. Does it increase the likelihood that you're going to pick up sepsis in this baby or not? Sepsis in the situation of sepsis? No. So that test, that is serum bilirubin in that situation has got no value at all, which means the PLR of a serum bilirubin for sepsis situations in that baby is 1, which means the likelihood that the test may come high in a diseased versus a non-diseased is almost equal to each other. Whereas if you're going to do history, physical examination, CRP, blood count, and then culture or PCR, you're trying to increase the likelihood that this patient has got a disease, or you're going to decrease the likelihood, which means you're going to rule out the disease. Okay. So you're starting off with a pre-test probability in your mind. The pre-test probability is nothing but prevalence. Before you start anything, there is already a pre-test probability of a disease in a particular baby. That prevalence in that population. There is always a chance of 1% risk that a newborn coming into the OP may have sepsis, right? So that is your pre-test probability. Now, once he comes and sits inside the OP and he tells you, mother tells you that he's not feeling well, you have increased that possibility or they increase that probability to a post-test probability. So the test here was history. Okay. Then you have increased again the post-test probability by doing a physical examination. So finally, you make a whether a diagnosis of sepsis is there or not based on increasing the likelihood ratios. So you start with a pre-test probability, but you have to be able to multiply it by a likelihood ratio, right? To make it into a post-test probability. And here again, math will come into the picture. You cannot multiply a
Just
probability
a
or a
second,
proportion.
Femitha ma'am. There's a lot of disturbance, ma'am. Dr. Janardhanan, please can you just mute yourself?
Yeah, when the remote is working, no, Gunjana, that button doesn't. Yeah, I managed that, I think, right?
Okay.
Yeah.
Yes.
Okay. Yeah. So it's fine now, no?
Yes, ma'am. You can go ahead.
So you cannot multiply a probability by a ratio because probability is a proportion and likelihood ratio is a ratio. You can't do that. So you have to first convert probability into ratio and then you can multiply it by a likelihood ratio. Now, this we did earlier already. How do you convert a probability into a ratio? You do probability divided by 1 minus probability. Just like how you did 90 and you did 90 out of 100, 90%. That we converted into a ratio, right? 90s to 10. So how do you convert a pretest probability into a pretest odds or a pretest ratio? Odds is a ratio. So you first have to convert a pretest probability into a pretest odds. Okay. So you convert that by pretest odds is equal to pretest probability divided by 1 minus pretest probability. That's exactly what you do for conversion of probability into ratio. You take the numerator and separate it from the denominator. So that's what you did. Your pre-test odds is equal to pre-test probability divided by 1 minus pre-test probability. Now you have made it into a ratio. So your pre-test odds you can multiply by your positive likelihood ratio because here now both are ratios and what you get is a post-test odds. Okay. But we still don't like odds. We like probability because we like to say there is a 60% chance, there's a 70% chance. We don't like to say there's a 60-40 chance and there is a 70-30 chance. We like to say 60%, 70%. So we always like to change it in our mind into post-test probability. So you do the same thing in reverse. Now you want to change post-test odds into post-test probability. Why am I going on and on about this? Because sometimes it comes in OSCEs. Okay. So you convert post-test odds into post-test probability by post-test probability is equal to post-test odds divided by 1 plus post-test odds. You just added or you combined the numerator and the denominator in this. So here you made it. This is a part of this now. Once more. Pre-test probability, which is actually prevalence when you start with it. But later it becomes different. Okay, so pre-test probability, you want to convert into pre-test odds because you want to multiply it by a ratio, which is a likelihood ratio. So pre-test odds is equal to pre-test probability divided by 1 minus pre-test probability. So you converted a proportion into a ratio now by separating the numerator and the denominator. Now you can, what will you get? You will get the result as a post-test odds. Sorry, you will get a pre-test odds. So you convert now pre-test odds into the PLR of whatever test you're going to do and get a post-test odds. So you had a particular odds before you did the test. You did the test and you multiplied it by the likelihood ratio of that test and you converted it into a post-test odds. Now, this you don't want because you don't like odds. So you convert post-test odds into post-test probability. So post-test odds divided by 1 plus post-test odds is equal to post-test probability. Okay. So suppose you started with a pre-test probability of 1%. That means that the chance of sepsis in that baby was 1%. But you did a very fantastic test which has got a PLR of say 40. Okay. What was PLR? Likelihood that a diseased patient gets positive result divided by likelihood that a non-diseased patient gets positive result. So sensitivity divided by 1 minus specificity. So if your PLR is high, it's a good test. So you have much more than 10, more than 20, even better. So if you have a test which has got a PLR of 40, then you multiply that 1%. You can't multiply straight 1% into 40 because 1% is a proportion and PLR is a odds. So you convert this pretest probability into pretest odds first. Okay, so that is 1 divided by 1 minus 1% divided by 1 minus 1%. That's how you convert it into pretest odds, multiplied by 40, get post-test odds, and then you convert that post-test odds into post-test probability. So now your probability has probably gone up to say 90%. So that because the PLR is so good, you have almost sure now that this patient has got the disease because you did that test which has got a very high positive likelihood ratio. Similarly, negative likelihood ratio. So in negative likelihood ratio, you don't want diseased people to get negative result, right? So the probability or the likelihood that a diseased patient gets a negative result divided by the probability or likelihood that a non-diseased patient gets a negative result should be very, very low. So the NLR as low as possible is very good. Okay, so in our mind, we usually use PLR because we do test to find out disease rather than to rule out disease in the true sense when you're starting next to the patient. Okay, so recap quick. Sensitivity, all diseased people, how many get test positive? Specificity, out of all non-diseased, how many get test negative? A PPV, out of all positive results, how many actually have disease? NPV, out of all negative results, how many do not have disease? PPV, NPV depend upon prevalence. We saw that. PPV will be very high if the prevalence is high. NPV will go up if the prevalence is low. PLR is a ratio, positive likelihood ratio. It's a ratio of two proportions. Likelihood that a diseased gets a positive result divided by likelihood that a non-diseased gets a positive result is PLR. NLR, likelihood that a diseased gets negative result divided by likelihood that a non-diseased gets negative result is NLR. You want good PLR, it should be more than 10, more than 20, more than 40, whatever. Higher. Anything that's close to 1 is absolutely useless because the likelihood that diseased fellow will get positive is equal to likelihood that non-diseased will get positive. Okay. Now, sir told us about ROC. Sir told us that when you have different cutoffs, you want to draw an ROC curve. That is a good trade-off between sensitivity and 1 minus specificity. So the further here, the point is, it means that the sensitivity is very, very high, correct? But your 1 minus specificity is also very, very high, which means that specificity is extremely low. That would make for a good screening test because you have high sensitivity, but you have very low specificity. You come down. That means you actually raise the cutoff if the test result is a positive value. Then you come down on sensitivity, but you are also increasing the specificity. But if you want a good trade-off, you take the shoulder where you get a good balance between sensitivity and 1 minus specificity. So this means that you have a high specificity, right? This way is bad specificity. This way is good specificity because it's 1 minus specificity. And you have this way good sensitivity, this way bad sensitivity. So you want it that way also and you want it this way also. So this would be a good cutoff. So you can draw an ROC, but you have to first put in, when you're making an ROC, you have to always be sure that a higher value is giving you a good, prediction of disease or a lower value. There are some like that, right? Like for example, if you have a low value, like in metabolic bone disease, say, if you're using phosphorus as your diagnostic test, if you have a low value of phosphorus, the patient has a disease, correct? It's opposite of what you find in most other cases where if you have high value, like if you have high CRP, then you have sepsis. So you have to be sure which one it is when you're drawing your ROC curve. You have to put it there, whether high value gives disease prediction or lower value gives disease prediction. Then only the graph will come out correctly. So that is for research purposes when you're drawing the graph. So there are situations, just remember that point, that there are situations where a lower test result may actually be indicative of disease as against a higher, which is what we are mentally used to. Okay, 2 more terminologies and I will stop. Or should I stop, Kunjana, already?
I think it's like 2 more terminologies. We can take it up, ma'am. I don't think so will be an issue.
Okay, so just 2 more terminologies. One is accuracy. Accuracy means that how good the test is as compared to the gold standard, or how good the test is as compared to the universal truth, which means that all of the test results, if you put together, okay, the true positive and the true negative alone will come on top. Okay, as compared to true positive plus true negative plus false positive plus false negative. So if it's a very accurate test, these two will be almost zero, which means the accuracy will be almost 100%. That's one. Okay. The other is one that might come in exams. That's called as a Jordan's J index. This is also used like similar to accuracy. It's sensitivity plus specificity minus 1. Which means that if you have sensitivity 100, which is equivalent to 1 actually for us, and specificity 100 or equal to 1, okay, then the best test will have 1 plus 1 minus 1, which is equal to 1. So your Jordan's index closer to 1 is good. If your Jordan's index is much, much, much further away from 1, then it is not good. I think that's enough, Nidana. Yeah.
Thank you, ma'am. Comments from Sourabh, sir.
Yeah, firstly, Femitha, I think you did a fantastic job. You explained everything very beautifully and in a very simple fashion. I don't have much to add, just a few points. I wonder whether you can just get back to that, or maybe you can just draw it out, that 2 by 2 table where you had your 10 and 90 and
Okay, sir. Oh, sorry. Have I stopped sharing? It's coming now?
It's coming, it's coming.
So the same numbers?
yeah, same numbers.
Sir.
Yeah. So in a situation like this, where the investigator is selecting how many diseased patients will be taken into the study, how many non-diseased patients will be taken, there we are artificially creating a prevalence. This is not the natural prevalence of the disease, right? I mean, I could have taken 100 diseased, 100 non-diseased, but that doesn't mean that the disease normally has a 50% prevalence amongst those who present with diagnostic uncertainty. So every test has to be done only in those who have diagnostic uncertainty. So what happens is, from this kind of a study where where the investigator has selected how many diseased, non-diseased, the positive and negative predictive value actually cannot be calculated because the prevalence has been artificially created, right? So ideally speaking, a diagnostic test accuracy study, you should recruit only patients who have diagnostic uncertainty to start with. So everybody who has diagnostic uncertainty undergoes both the index test as well as the reference standard test, or which earlier used to be called gold standard test, but the current terminology is that it should be called reference standard test, because there is really no such thing as a gold standard test. Today's gold standard may be replaced by tomorrow's gold standard when we have a better understanding of the pathology of the disease. So so it should be done in all those who have diagnostic uncertainty. Then one gets to know what is really the prevalence of the disease in patients who present with diagnostic uncertainty, and one can calculate the predictive values. That's just one little point I wanted to make. The second is, uh, this conversion from probability to odds and odds to probability does get a little confusing for beginners, and most physicians are mathematically challenged. So that's probably one of the reasons we took the NEET entrance exam instead of JEE. So one guy called Fagan, he made a nomogram which simplified all of this. That you cut through the all that calculation stuff. And with your permission, I'll just show you the Fagan's nomogram once. I'll just share Fagan's nomogram. Is it okay, Gunjana? If I
Yes, sir. Yes, sir.
Yeah, it just take 2 minutes.
Sir,
And
I'll just
Mm,
stop
make
sharing.
her the co-host. Yeah.
Sorry, sir. Sorry.
am I sharing my screen now?
No, sir. I need to stop. Yes, sir. I've stopped now.
Yes, sir. You were sharing.
Am I sharing?
Yes, sir.
Is it visible?
Yes, sir. Yes, sir. It's visible, sir.
Yeah. So there's this fellow called Fagan who published this nomogram in NEJM years ago, which everyone uses now. So it has three vertical things called the pre-test probability, the likelihood ratio, and the post-test probability. So all you need to do is to take the prevalence or the pre-test probability of the disease, and if you get a test positive, say in this case CRP, if it has a positive likelihood ratio of 3, you just take a ruler, draw a line, and see where it is cutting the post-test probability line without bothering about the odds and all, because that has already been built into this nomogram. So you directly calculate that, okay, the post-test probability will be 60% of having the disease if my CRP is positive, provided I started off with a 30% chance of disease to begin with. And on the other hand, if my CRP is negative and the likelihood ratio of a negative test is for say zero point 0.3, then I again take a ruler, draw a line, and now I get a 10%. So all that thing of having to go via odds is kind of taken care of by this nomogram, which really simplifies matters. So, most apps these days allow you to do this direct calculation of the post-test probability. So that's something which, can easily be done. And regarding the Udens index, that is something which is typically used for a test which is numerical rather than binary. So at each cutoff, your software program will calculate the Udens index, and the cutoff which has the best Udens index is usually the most optimal cutoff. It gives the best trade-off between sensitivity and specificity. So the one that gives you the highest Udens index. Yeah. Just these are a few things that I wanted to add. I think you can take questions. I'll stop sharing.
If you have any questions, you can put it in the chat box, or I think you can even unmute yourself and ask.
Okay, thanks to Yashwant and Abhishek for calculating, and KS also for calculating the PPV and NPV in the chat box. I'm seeing it now only. It's a total bummer thing to do on Valentine's Day, Saturday night, right, sir?
It was the wrong guy, I suppose.
So all those who are single have turned up.
I think there are no questions as such in the chat box.
Then we'll probably wind up, sir.
Yeah, okay, sure.
Thank you so much, sir. Thank you so much for being there and for helping out and for adding.
Thank you, sir,
Okay,
taking out time, and we'll be disturbing you more for such more sessions later in
okay.
the future. And thank you, Dr. Femitha, for such a wonderful session. I think it's something which we thought of starting it, and just for a kickstart, a lot of glitches and everything, we were able to start this. But I think this is going to be useful. Maybe we are not good at statistics at all. Many of and the calculations are, for the DM or for DRNB students, it is important, but most of the time, the people do skip that. But let's see how the further session goes, and we'll be inviting you, sir, for the more sessions, and we'll be needing your support for this. So thank you for coming, sir, and we'll be bothering you more, sir, in the further sessions.
Okay, no problem. Thank you.
Good night, sir. Thank you.
Thank you, Pamita, ma'am. Thank you, sir.
Thank